our experiment today, you can get the code. As I said, I already uploaded all the code in Microsoft Teams, so you can get the code from the Microsoft team. And first of all, I would like you to test your system whether you have the compiler or not. How to do it? You can just simply use the command like this, GCC. You just type GCC and let's see the output. Here is the warning, is the error, complaining something, the system complaining something. And here it said that no input files, meaning that I already got the GCC compiler on my machine. In case that if you don't have the warning or the error message like this, you may have to install the GCC first. To install the GCC is very easy. You know how to do it, right? In Linux, especially in Ubuntu or in CentOS or in Red Hat, we can use we can install many things from the online database. In case of Ubuntu, you can use the command like this: sudo apt install gcc, and that's it. And don't forget that your machine has to connect to the internet. That this is the command we use to install the C compiler into our Linux. Okay. Still anyone need help? Next, we are going to compile the code because the code that I uploaded to Microsoft Teams, they are just the short code. They are not executable yet. So you have to compile it. To compile the C code is, you may say that it's quite simple, or you may say it a little bit complicated if the system is very big. But our sample code here are quite small, not quite small, very small, very simple one. So to compile the code is very easy. Go to the folder that you just saved the short code, and then use the command like this, gcc, and then followed by the file that you want to compile. In this case, I would like to compile zombie.c. And then I can press the enter straight away, and I will get a.out if successfully compiled. But instead of getting the default name, I would like to specify the output file name. I can use the option O to specify the output name. In this case, I want to get the zombie.o. This is how we compile it. We use GCC followed by the short code, and then we can have the option, let's say -o, to specify the name of the output. I press enter, and nothing happened. If nothing happened, you are lucky, because it means that the system can compile your code. If you got lots of messages, meaning that you may have some warnings, errors, and whatever that the system can notify you. You can use the command ls to check whether you get the zombie.o or not. And in my case, I get the zombie.o. And you notice that the file name here is in green, meaning that this one is executable. It is an executable file. When it is the executable file, it means that I can run it straight away from the command line here. Let's say if I would like to run, I can run in any Windows here because in Visual Studio Code also have the terminal. I can run on the terminal in Visual Studio Code as well, or I can run it in any terminal. Okay. Look at the result here. I run the zombie.o. When I run the zombie.o, I would like to see what happened. So now I haven't started running the zombie.o yet, but I would like to show you the ps command. The ps command, we use it to see the process in the system. And you can have many options. It depends on what you want to see from the result. I use the ps followed by the -o, and then PID, PPID, SID, stat, home, and then capital C, and then zombie.o. This is the command that I would like to use to see what happens if I run the zombie.o. But before pressing the enter of the ps command, I have to run the zombie first. Okay, I run the zombie.o. I press enter here. So zombie.o is running now. Now I would like to see what is going on in the system. And in the system, I use the ps command, and I can see that zombie.o, we have two processes here. The status of the first process is S+, and the state of another process is Z+. And I can see the PID, I can see the PPID, I can see the SID. In Linux process, there are many ID associated to such process. For example, here you can see at least 3 IDs. The PID, which is the ID for that particular process. PPID is the ID of the parent process. And the SID is the session ID. And you notice that the SID here is the same as the PPID here. It means that the parent of this process is the session it is in the same session. You can notice that here is because we run this program in the terminal, and probably terminal is the session ID of it is the session leader for these two processes. Okay. And here in this zombie process, we have the PPID 140586 in my case. In your machine, you will have the different number from mine. In my case, I have 140586, which is this one, meaning that the first process is the parent of the second one. But you don't you don't get any result from the PS command, right? It's just because you have to run the zombie first and then straight away go to the PS command. Otherwise, you see the code here. Before seeing the result here, let's look at the source code here first and try to understand what is going on inside. We can have a look together because this is the very first file that we tried together. So shall we look at the source code together. In line 7, we define a parameter here, a child PID. This is the first variable that we define in this simple program, and we assign it with a fork function. At the same time, we create we create a child process, and then we assign the PID of that child process to this parameter. In line number 9, what happened here? In the parent process, the child PID will have some number that greater than 0, right? So meaning that in line number 9 and line number 10, in the parent process, it will execute these 2 lines. But what happened to the child process? The child process will have the child PID parameter as well, but the value of child PID in child process is 0. So the condition here is not correct. In child process, it will execute on line number 13, right? From the source code like this. It just exits. So it just terminates straight away after fork. So if you would like to see something like this, you have to run the zombie code. You have to run the zombie and go to the PS command straight away so that you can see. Otherwise, you can see the code here easily for 50 seconds. So if you cannot finish the PS command within 50 seconds, you won't see anything there. Any other question? The question is about, do we have to run a zombie and the PS in the separate terminals? In this case, yes. Otherwise, you cannot see the result from PS command. Why do we have to run the zombie code in the separate terminal with the PS command? It's just because as you see at the code here will be terminated very soon, within 50 seconds. It will finish, and you can see no more the process from the PS command. Okay? Because the PS command will show the running process. When it finished, you cannot see from you cannot see anything from the PS command. It's real time. You can use just only the PS command, and you can see the result. Here is the PS command, but you can provide more option, for example, PS, and then you provide the option A. When you provide the option like A, you will see all the processes that are running in the system. Oh, AU maybe. Lots of possible options. You can look at the menu if you would like to see the possible options. Here are the example of what is in PS command. Here is just only the meaning of the status, and you can see you can have the status like this. And previously we have the status like status of the process like this. Z and then plus, S and then plus. If you would like to see, if you would like to know the meaning, you can use the manual to see the what is going on there. You can see the explanation. For example, here Z is the defunct or zombie process, and the plus sign meaning that the process is in the foreground. That is the example. Okay, you can use the manual page to look at what the possible option that you can use. You can use man and then PS to look at the to look at the menu of the PS command. Okay, but I won't go through all the options. If you would like to try it, you can try it by yourself. Okay, that is the zombie. So when you develop a program in the system, try to avoid creating the zombie process like this. Now, you may notice that if I use the PS command again to filter out just only the zombie process, no zombie.o anymore because zombie.o already finished. It's already terminated. So right now I cannot see zombie.o from the PS command anymore. You can see what is going on in your system by using other commands. For example, you can use the command like top, top. You can use the command like pop, top, and then present tab. You can notice that, oh, this is you can see the processes and how the system use in terms of CPU percentage, CPU utilization, memory, and swap file. This is a very simple tool to monitor your system. Okay. To get out from the system monitoring top here, you just press Q. You just press Q, letter Q to finish. Any question about the zombie process? So next, we are going to look at the orphan. here is a code for often. What's the difference between the zombie and often? How about look at the code here? The code here is quite simple, right? Look at the line number 9. We create a child process, and the PID of the child process will be assigned to this variable PID. So the line 11 to 15 is for the parent process, and the line 17 to 20 is for the child process. And what happened here? In parent process, just print the PID of itself, right? Because we use the get ID function, and to just print the ID of the parent, and then print ID of the child process, and then sleep for 20 seconds. That is the parent process. But how about the child process? It just sleep for 30 seconds. So probably and mostly the parent process will be terminated before the child process, right? And we don't have the wait here. We don't have the wait here. So the child still alive without a parent. That is why we call this process will be the often. Try to compile and run this code. It's quite simple, right? You know it. GCC and then often, and then you can use -o to specify the output file name. Let's say we can use the same name, but instead of .c, we have .o there. Or you can use .out or whatever you like. If you didn't change anything, you should successfully compile the code. And then you just run it. And before running the code, you may have to set up the ps command, what you want to see. For example, I can use the same command as zombie, but instead of provide the zombie.o, I filter everything with the often.o, something like this. I prepare the ps command first because the code here, often.o, will run for a few seconds, will run for 20 or 30 seconds, and that's it. So I would like to see what happens. So I prepare the ps command. When I prepare the ps command, when I ready, I just run the often. I just run the often.o. When I run the often.o, I can go back to the ps command, and I can see ps here. There are two processes. And we know that this will sleep for 20 seconds. And then it's done. The parent is done, but here I run again. I still have the often.o. You notice that I still have the often.o. The parent already finished, but the child process still there, and I got the result from the child process there. But if I run PS again at this time, because the parents already done and the child also done, I should see nothing there. Now I cannot see anything from the orphan process anymore. In good programming, it's better if you can create a process that cannot be the orphan process or cannot be the zombie process. Otherwise, your process table will fill up with the zombie or the orphan process, and that occupies some resources of the system. Any question here? The zombie process? The zombie process, you can go back to the code and you can, I believe that you can come up with the conclusion by yourself. Look at the code first. Here is the zombie process, and the line number 9 and line number 10 is for parent, right? It's for parent. And line number 12 and line number 13, or you can say that simply 13 is just for the child process. What happened here between parent and child? Parent still alive, but child exits first, right? Because parents still alive, just sleep. Just sleep meaning that it's still alive, but just sleep. Or you can say that it's doing something else. It's busy, something, right? But the child just finished. But it cannot notify the parent whether it's already terminated. That child is a zombie process. Okay? So zombie is a process that it cannot notify the parent about its status, whether it is still alive or it is already terminated. Because why it cannot notify the parent? Because the parent do not call, it does not call the wait system call. No, the question is the parent process can assume whether the child process is running or not. No, it cannot. The parent process don't know the status of the child process at all because it does not get any notification. The wait system call make the parent process and know the status of the child process. Without calling the wait system call, parent process cannot know the status of the child process. Well, actually zombie process can happen to any process actually, but to make the lifetime of assembly process shorter, it's better if you call the wait function in the parent. Otherwise, you will get lots of zombie process in the system. But most of the system automatically clear up the zombie process in some certain time. But it's better instead of using the automatic mechanism to clear up all the unused resources. It is better if you are a programmer, you notify the parent process that, oh, this child process already terminated, let's clean up. Yeah. At least in the process table. Any other questions? Shall we move to the fork.c? Let's have a look at fork.c. What happened here? We know that a fork function, we can create a new child process from the fork function, right? And the question is, what happened in the global and the local variables that define in the parent process? Can it be shared among the parent process and the children, or the memory space? The memory spaces are separated among the parents and the children. What is your guess? Can you follow my question? If we define the global variable, for example, in the code like this, in line number 8, we define the global variable here. It's named global var. It is the integer. And in line number 12, we have the local variable. I call it local var. And I assign the value 0 to local var. And in line 13, we have, I define the p, I define variable p as the pointer of integer. And I allocate 2 bytes from the main memory to this variable. Okay, so p can store integer. P can store integer. Local var can store integer as well, but it is the local variable. Global var can store integer as well, but it is the global variable. And now, what will happen if we fork? We create a new process, a child process. Look at the code here. We create a child process by using the fork instruction. And then we can assign, let's say, the value 0 to p. This is how we assign the value to p. We use star and then p so that we can assign the value 0 to p.
I got an issue with the code.
Right.
The malloc seems really dangerous. Are you sure you shouldn't be at least using size of int? I think it will crash on some computers.
Oh, really?
Yeah, so
Okay. How about yours?
why not just int p is equal to int? You don't need to int cast, but you can just do malloc size of star p. Just to make
Okay.
sure that it's large as p, because int is usually 4 bytes.
I see. All right. But in this case, I just try it on this virtual machine, and let's see whether it's still working or not. If it didn't, maybe we can change to what you suggested.
It's undefined behavior, so even if it works on your machine, it's not guaranteed at all to work on any machine.
Oh, all right.
Yeah, so I think it's for the best if you just use size of star p for the sake of safety.
Size of star P.
Yeah,
Okay,
for the moment.
that is nice. Okay, size of
Spacebar star p.
star P. Excellent. Okay, thank you. Okay, Paul just suggested that we should change from the number 2 to the size of star P, just in case that the size of integer is a bit different from 2 bytes. It depends on the platform that you are using. Okay, great. Before running the code, try to understand the process, what happened here. If sharp PID greater or equal to 0, so fork successful, what happened? If sharp PID is equal to 0, meaning that in this block will be executed just only when in the SHA process, right? So in the SHA process, we just update the local variable by 1, update the global variable also by 1. And then we update the P. We assign the 50 to P, and then P print it out, and then we assign P again with 200, and then print it out. Okay, that is the SHA process. But how about in the parent process? The parent process also assigns the value to local var and global var as well. And then assign a new value to P and print it out. Assign a new value to P again and then print it out. And that's it. So both parent process and the SHA process try to assign the new value to local var, global var, and P. If they share the variable together, we will see that the result from the output from the SHA process and the parent process should be the same value at some point, right? But if the values of the variable are totally different, meaning that they don't share the memory space. Let's try to compile this code and run it and see the result, and try to summarize what happened there. Okay, I compile it and then I run the fork.o. This is what happened to my machine. What can you see? Because there are two processes that they are trying to run at the same time. Maybe it's better if I allow one process to run before. Let's say if I would like the child process to finish first and then the parent process can run later. Because now here I cannot, because I cannot, what you can see here, if you see the result here, at the very beginning, the parent process has the local var equal to 0, global var equal to 0. Child process also have the same value. But next, what happened? Parent process has local var as 10 and global var as 20. But in child process, the local var is 1, but global var is 1. They are not the same, right? Local var is not 10 and global var here is not 20. So the assumption that I made about the memory space sharing is not true. If I assume that I have the local var, I have the global var, and I have P. If the child process and the parent process can share the memory space, meaning that one of them should have the same value. For example, if I assume that the parent process can share the memory space in global variable to each children, to each child, the global variable should have the same value between the two processes. But here, both a local variable and the global variable, they have different values. 10 in parent, 1 in child process, 20 in parent, and 1 in child process. And how about the P? Because P we use the memory allocation function malloc to allocate the memory, the space in memory. We can see that the address of P in parent is the same as the address of P in child process. The number here are the same. At the very beginning, the value is 0 and 0. They are the same at the very beginning. But when we change the value in the value of P in parent process from 0 to 100, the value of P in parent is 100, but the value of P in child is 50. What does it mean? Even the memory space, even the address, the same address of the parent process, we can have the same address in the child process, but the same address here is not the same physical address. What does it mean? It's not the same physical address. The child process and the parent process do not share memory space at all. This is from our basic experiment here. As you may realize when we discussed about the PCB yesterday, let's say the parent process is process 0 and the child process is process 1. They have their own PCB. Parent process has its own PCB, and the child process also has its own PCB as well. And they don't share the memory space at all. Not the local variable, not for the global variable, even from the memory, like pointer of integer that we allocate from the memory. Any question from this example? This is two different processes. There are two processes here. The parent process and child process. And each process has its own PCB. And when we talk about PCB, there's some program cover of itself, there's stack, and what else? Data section, text section, and heap, right? So the child process and the parent process do not share the memory space. The address here, the address here is the virtual memory. What does this mean, virtual memory address? The virtual memory address is the address that the system can see, not the physical address. The physical address usually is less than the virtual address. Let's say if you're using the 64-bit address, you can have the memory up to the power of 64 bytes, right? But most of the time in your system, you may have the memory, let's say 16 gig or 32 gigabyte, and that's it. It's much less than to the power of 64 bytes. But in address space like this, it is always a virtual address, and the virtual address is always a 64-bit. Okay, any other question? Maybe you have to, maybe this one is a bit too fast. You may take your time to sit and have a look what the result tell you, right? And try to think, try to follow what I just explained to you. If you can catch it, if you didn't catch it now, maybe you have to take your time to look at the code, look at the result, and you may realize that, oh, this is quite simple. And the next one, we can create more than two processes, not just only parent and child. We can create, let's say, the next one is the fork order.c. Now we are creating four processes. As you may notice that here, in line number 10 and 11, we have two fork function. The first one, we create the first child process here at line number 10. And with line number 10, we have the first child process. And the first child process also have the code on line 11. What does it mean? It means that the first child process can have another child, right? And do you get that? The first child process can have another child because in line 11, the child process, the first child process also have the code in line 11 as well. Okay. And the second child process we created from line number 11. So in total, we have 4 processes here. So we can use the ID number 1 and the ID number 2 to identify what the process that we are focusing on. For example, if the ID is greater than 0, both ID1 and ID2, meaning that here is the parent process, we can run this code. We call wait system call 2 times to wait for ID process child to wait for first child and the second child. To have a code for the first child, we can test whether ID number 1 is equal to 0 or not. If ID number 1 is equal to 0 and ID number 2 is greater than 0, meaning that this is the first child process, here is the code for first child process. And here is the code for second child, because when ID number 2 is equal to 0, meaning that here is for the second child process, and the last is for the child of first child process, or we simply call it grandchild. Here is the example of how we can create more than 2 processes. In this case, we have 4 processes. And what happens if we create more than 2 processes? What the order of the process that can give us the output? You notice that in the parent process, we call wait 2 times. These 2 times for the first and the second child process. And in the first child process, we call wait just only 1 time because it has 1 child. We call wait 1 time. But in second child process, there is no child, so we don't call wait here. And definitely, the grandchild process does not have any child, so we don't need the wait system call here. Let's see what happened here. I just compile it. And try to run and see what is going on there. The grandchild process terminated first, and then the second child process, and then the first child process, and then the parent process. This is the result that we get. I just want you to see the order. What happened if you have many processes in your system. And in case that you have the wait of function in the parent process, what will happen? Why it happen like this? It's just because you call the wait function first, right? You may notice that in parent process, you call the wait function before the printf. If you call printf first, it does not guarantee that this one will be the last one. But when you call wait first, it guarantees that the printf will be executed the last until the first and the second child processes are terminated. This is the result from function weight. Is any question? Sleep is just, you can say that you, actually, you can have lots of instruction here, but instead of putting a lot of instruction, I just use sleep to assume that it can do something. But in reality, it just put the process into the sleep mode or into another queue. And we can wake it up when the time finish. When the timer finish. But you don't have to use the sleep. The sleep here just to let you to allow you to see the result that is coming up. It's a kind of simulated what is going on in the first child process, in the second child process, something like that. Any question? Why the second child does not have a child? Look at this one. The line number 10, we call the fork function. What does it mean? It means that we create the first child here. And the code after this will be duplicated to the first child. What happened to the first child? It will have the code from line 11 until the list. So the first child will have the line 11 as well. But how about the second child? The second child start here. We created the second child at the line 11. It means that the second child will have whatever after this. Meaning that the second child will have the code from line 14 onward. And from the line 14 onward, there is no fork, no more fork. Okay. That is why the second child does not have a child process. The number of process will be number 2 to the power of fork. No. It depends on how you put the fork instruction. It depends. You can have the fork instruction like this. You can have the, let's say, y, y, fork go to 0, and like this. You may have something like this. So it depends how you put the fork in your instruction. It's not necessarily the number of the process equal to the power of number of forks instruction. All right, I will take a break for 15 minutes and then we will come back to look at the simple inter-process communication. I think it's simple. Okay. But at this time, if you need some help, just let me know or your PA know. Okay.
Yes ค่ะ
All right. So the next is the simple inter-process communication. As we discussed previously, that the memory space between the parent process and the child process, they do not share the memory space. The parent process have their own memory space, and the child process also has its own memory space, so they don't share. How can we send a message or send the data between the parent and child processes? Here is a very simple approach, which is the shared memory. We can create a shared memory object. Here, okay, come on in. Let's have a look at the very first lines here. We define size as a constant of integer and the size, and we assign 4k to the valuable size here. We have a pointer of character name, and we assign the value OS to it. And we also have a pointer of character again, and this is message 0. And we assign hello, the string hello, to this variable. And in line 13, we define the message number 1. This is also the pointer of character as well. And we assign the string world to message number 1. You may think that this is very similar to other languages. For example, in Java, we define it as string. Or in C#, we define it as string. But here, in standard C, we use the pointer of character to define a variable that can store a string. But this one is just constant string, meaning that we cannot change the value here. In line 15, we have shared memory file descriptor. We name it as SHM50. And in line 16, we have the void pointer. This is a special type of the variable. And in line 18, we initialize the shared memory file descriptor by using the shared memory open function. And you notice that we provide the name as the parameter. And this is the flag that indicates what we want to do with this shared memory. In this case, we would like to create and we would like to read and write to that shared memory. And next, we have to specify the size of the shared memory. In this case, we use the ftruncate function to define the size of the shared memory file descriptor. So we provide to define the size of shared memory. So we provide the shared memory file descriptor as the parameter and the size. Or we can simply say that we would like to allocate, or we would like to create a 4K memory as the shared memory object. And next, we use the function mmap to get the address of this object. Because we allocate the memory 4K, and now we want to know where it is. So we use mmap to get the address, and we assign that address to our void pointer, PTR. And what is next? We can write to that address by using sprintf, and then we write whatever we want to that address. In this case, we want to write the string in that address, and here is the string with the format %s here. But instead of writing the %s to the memory, we assign the value of message 0. Or we can simply say that we write the string hello into that memory location. When we write the hello into that memory, the pointer is still unchanged. So the PTR is still unchanged. So we have to update the PTR to the next location. How can we update the PTR to the next location? It's quite simple. We can find the string length, the length of the string of the message 0, and then we update so that we can update the value of the PTR to the next point. When we update the PTR to the next address, we can write more data into that address. And we use the same function as printf. And then we write the message number 1 into that address. And then we're done. The last line here, you can update the PTR, or you just leave it there. It's up to you. But in this case, we update the PTR to the next location. The question is, let's say in line 23, if we don't update the address of PTR, what will happen?
We'll get
PTR
override.
is just, right, it will be overwrite. Yeah, we will overwrite the data in that location with the new one. Okay. So this is how we allocate the memory, and we put the data, write the data into that memory, and that memory, we can consider it as the shared memory. So we have to run the producer first. So the hello world will be in the memory, and then we have to run the consumer later to read the data from the shared memory name OS. So now I want you to look at the consumer. In consumer, we are going to do almost the same, but instead of creating the shared memory object file descriptor, shared memory file descriptor as the read and write, now we use the flag read only. And here, how can we know that we are going to read the same location? We have to use the same name here. You notice that the name here is OS, and then we provide the name here. And again, we use the nmap to get the location or the address of that memory. And then we can use the command printf. And the printf is the print format. And here we convert the pointer into the to the pointer of character, or we can simply say that this is a string. So this string will go into %s, because %s is just like a placeholder, right? So basically, it will read any string in that location and put it into printf. So we expect to see hello world from the consumer, right? And then we can delete the shared memory by using the shared memory unlink. Okay, any question before we running our code? Okay. We just compile the producer. Oh, I have to use the flag LRT to compile it. Because we are using the shared memory, so we have to use the flag LRT. And likewise, I'm going to compile the consumer as well and use the flag LRT as well. Okay. And then I am going to run the producer test. So I'm running the producer. When we run the producer, nothing happened because we just write two strings, hello and world, into the shared memory. So nothing appear on the screen. But when we run the consumer, it will read the data from the shared memory. And with the line number 15 here, it will show the string that it can read from the shared memory and print it out on the screen. It should be hello world. And here what we got, hello world. This is how we create the shared memory. How can we put the data into shared memory and how we read the data out from the shared memory. This is a very simple way to, I say simple because the code here is simple, but actually this approach is not that very simple. It's quite hard to debug, and it's quite hard to, it's easily to forget to unlink the shared memory. Actually, it's prone to get the error. But with the sample code here, you notice that it's quite not that very complicated. You can try it with a few lines of code. This is one way that you can share some data between two processes. Any question here? It just like we have two different processes, and be trying to let them to pass some parameters between them. In this example, we just write the string into the shared memory, but you can write any data into the shared memory. It depends on what you specify in the producer. this is how you specify, this is how you write the string into the share memory, right? You write the string into the share memory, so you get this string. You can try something else. It may work or it may not. Let's try. And the last one for today. Any question before we are going to the last? I can feel that some of you feel very happy. Oh, this is the last one. Yay. And can many processes open the share memory at the same time? What do you mean open? Read or write? You can read, you can have many processes that read the memory object at the same time. You can read. But when you write to the same memory object with multiple processes, it's better if you lock it to one, to get one process to write to that memory object. When it finishes, let other process to do later. Otherwise, you will get conflict. To delete the share memory. Otherwise, the share memory is still there. In terms of process synchronization, we will discuss about that later. We will have a very complicated problem. We call it what is called
Race condition.
oh yeah, rest condition. Yeah, rest condition is, yeah, you can say that. Yeah, we will have the rest condition. If you're trying to write to the same location with multiple processes. Okay, last one for today is the pipe. This is another way that we can share the data or send the data between processes. Previously, producer and the consumer, they are totally different processes. They are not child, they are not parent, they are just different two different processes that would like to read and write the data. But here is the example of parent and child process. And we can use pipe. Look at line number 14 and 15 here. We have the FD. We define it as the array of 2 elements. And we can pipe FD. And after that, we can use the fork, the same as what we have done before. After this, what happened? We will have the process for child and the process for parent. And definitely at the line number 18 until the line number 38. 18 until 38, they are for parent. And after that, they are for the child process. And what is going on here? Let's have a look. In parent process, we call the weight. Already, you don't have the pipe. Let's see in oops, no pipe. Okay, just a second. No pipe. Oh, is there? Okay, I just uploaded the pipe.c. Okay. Let's have a look at the line number 18 until the line number let's look at the child process first. Let's see at the line 39 until line 52. In here, because the PID is equal to 0, the code here is for the child process. We define the array ARR and assign the value 1, 2, 3, 4, 5 to this array. And what happened here? Because we pipe the FD, so we just write the array to the pipe by using the function right here. What does it mean here? We have array 1, 2, 3, 4, 5. So we create the pipe that have 5 elements and 1, 2, 3, 4, 5. And look at the parent process. Parent process will wait until the child process finish, meaning that the child process already write 1, 2, 3, 4, 5 into the pipe. And what happened here? Because we know that the array in child process and the array, if we define an array in child process, we cannot read that array in the parent process. So we can have a separate local variable here for the parent process. So ARR here is definitely the different variable from the ARR of the child process. And we can read from the pipe to the parent process. And because it is the array, we can use the for loop to read the data from the array ARR and try to get this one. And this is one way that we can share the data between the child and the parent process. Okay, try this one. GCC pipe. Pipe.o. And here the result of pi.o. And we get 1, 2, 3, 4, 5. And this is the value that the parent process can read from the pipe. Previously, when we practice on the basic command in Linux, we use the pipe. For example, we can have PS, AUX, and then we have pipe like this, right? And then we can use something like a regular expression to fill out the result. Let's say I want to see some process that starts with my name, let's say. This is the example that we use the pipe in the normal Linux instruction. But we can use the pipe almost the same in C programming as well. And this is how we can use, how we use the pipe in C programming. You can go through the API, for example, the DUP, DUP, and you can go through the API like pipe. Let's say if you want to see what happened there, you can look at the menu. Let's say if I would like to see what happened in pipe, I can man pipe like this. And you can go through all the description here, and there might be example how to use it. Okay. And this is the example of how the parent and the child process communicate to each other. I hope this is a hint for the assignment number 7, because in assignment number 7, we ask you to create at least 2 processes, one parent process and one child process. In the parent process, you have to handle the input from the user. For example, you can read the number n from the input or from the command line argument. And then you have to pass that number n to the child process. The child process has to use that number n to calculate the summation of from 1 to n. And finally, the child process had to pass the summation back to the parent process, so the parent process can show it out on the screen. That is the question of assignment number 7. Any question? I just think that the API here is just new for you, and that's it. Nothing complicated. It's just new. When you get used to it, you feel, oh, this is okay. That I just never used it before. Today you feel, oh, it's a bit complicated. It's just because it's very new for you. Some of you may feel something like that. But if many of you ever used the C programming before, get used to the C programming, you will feel that, oh, this is quite common. Okay. Do you still thinking that software side is better than hardware? Maybe not anymore. All right. If you have any question during week, you can ask me how to go through the assignment number 7. And but first of all, I would like you to try by yourself first. Try to figure out how can you communicate between the 2 processes you have, parent process and the child process, and how can you pass the data or parameter between them. And try by yourself first. You can use the shared memory object like the previous example, or you can use the pipe as the last example. But the last example, the pipe just passed the array. But here we don't have to pass the array. In the assignment number 7, you just pass only one variable, right? You pass only one variable. But you have to pass back and forth. Hope you enjoy the assignment. All right. Any question from student on WebEx?
Just a little concerned over the fact that the memory management and system calls are a very in-depth topic in C, and I feel like they're not appreciating the basics of C itself. So the
Mhm.
usage of all of the system call functions would be very limited.
I see. Mm-hmm. I see. Yeah. Yeah, I will think about it and let's see what can I do for everyone for the next time. Any other concern or and questions? All right. So thank you very much, everyone. And as I said, delete the read. If you still have any difficulty on the assignment number 7, just let me know, okay? Just ask. But first of all, I would like you to try by yourself first. Try to search through the internet, looking at the API, how to use it, and try again and again until you feel until you're struggling with the problem you can solve, you can ask, okay? All right, see you next week.
Thank you for today ค่ะอาจารย์